Okay, welcome everyone to my continuation of what is geometric topology. Last time we have seen some fun with what you can do with surfaces, like you knot them in R4. And today I would like to tell you more fun what you can do with surfaces. In the last time it was more like there's an open, really nice open field of mathematics where not much is really known, movies and colors. This time it's more like a very surprising, like you make it more complicated apparently, but it gets easier and you have a really beautiful theorem in the end, which is called the Heawood theorem. Okay, today's topic is the chromatic number of a surface. What could that be? Well, we'll see, but it certainly involves graphs on surfaces. So let's have a look. So a graph, okay, a graph is a one-dimensional object, so you can think of it as embedding it somewhere, and you would like to embed it such that no intersections of edges appear. Turns out that you can always do that in 3 space, not necessarily in 2 space, but you can always do it in 3 space. And the proof that you can always do it in 3 space is so amazing that I'm going to show it to you right now. So take graph and you want to embed it in 3 space such that no self-intersections, no intersections of edges. So what do you do? Well, you consider a book, really just a book. Here's a 3-page book. All right, so here's a sheet, here's another sheet, here's another sheet, and here's the binding of the book. Okay, so you just put all of your vertices, this one, whatever, to somewhere. You just put all your vertices along the binding and so on. So let me just do it. Here's another binding vertex. I have red still, another binding vertex, and I have black, another one. And then you can just make sheets, and you can make as many sheets as you want. So the book has as many pages as you want. Let's say finite, but you only need finitely many anyway. And if you would like to, you could draw every edge on a separate sheet to make sure that they don't intersect. This is a little bit more efficient, this picture. It still has no intersections, but it draws more than one edge per sheet. But if you really want to push it and just want to show that something embeds in R3, you can just make one page of your book per edge, and obviously it won't intersect because it's a book and the pages are different, and well, it certainly fits into 3 space because it's a book, and we all know that books live in 3 space. So you can embed every graph without self-intersection into 3 space, which is pretty cool. Which is a pretty cool proof. Just a book, and books live in 3D, and that's it. And just one page per edge. But well, what about embeddings? So in R2, this is not longer true. So what about graph embeddings in a surface? So for a general surface, it's already not true. A surface is 2-dimensional. It's 1 dimension fewer than our good old friend here, R3, and you clearly can't play this book trick anymore. So what about graph embeddings in surfaces? Can we say anything about them? And here comes an idea. So graphs on surfaces. So here's a graph. Quite complicated, but I claim on the surface, which is actually the torus. The torus is a surface where when you exit here, remember, you enter here, and if you exit here, you enter here. So it's this little a picture of a torus. Like if you just take it and build it out of paper, you will see that this is a torus. So if you wrap it like this, you get an annulus, like a cylinder. And if you identify the 2 points of a cylinder, you get a torus. Anyway, so this is a slightly strange picture. So the vertices here are just the intersections here. So the endpoints of the hexagons. And well, the edges are just the edges of the hexagons. This is this graph here. So let's try, well, it's a staring exercise, but let's maybe try to see it. I claim this picture has a lot of hexagons, as this picture, obviously. So if you start here and just walk along, let's say to here, this is 1, 2, 3, 4, 5, 6. So there you have a hexagon, and it will somewhere end up here as being a hexagon. So the left-hand side is a graph, and the right-hand side is an embedding, a crossing-less embedding of the graph into the torus. And you can try to, well, see that this graph actually does not embed into R3 or the sphere, which is kind of the same anyway, without crossings. So that's an interesting problem to just fix a graph, and what is the minimal embedding, well, what is the minimal surface that the graph, given graphs, embeds to? That turns out to be a very hard problem. So for a fixed graph, finding the minimal surface where it embeds to is quite complicated. But the opposite problem is kind of easier. So if you fix a surface, we can say quite a lot. So you fix a surface and you study all graphs somehow that embed into the surface. Okay, here's an example of that. So if our surfaces are R2, our good old R2, or S2, like a map on our globe, right? R2, a flat map or a map on our globe, and you have a graph on it. That's called a planar graph. If you have a graph on it, it always divides, well, this is a very boring graph. Here's maybe a more exciting graph. It always divides R2 into those little regions here, and you could think of coloring the regions. And the rule for coloring is that whatever I did right now was really silly. The rule for coloring is that adjacent faces should get different colors. So everything here is adjacent to the outside one, so I can't use the same color again, but for example, I could make this blue. And then there's this famous theorem, which goes back quite a while as a conjecture, which is called the four-color theorem, that, for example, the minimal number of colorings you ever need for everything that embeds into our good old friend, this one or this one, right? The maximal number of colors you ever need to color a real map, like flat mud or on the Earth, surface of the Earth, is 4. It's called the four-color theorem. And I would like to ask the same question in general. So for a given surface, we only study embeddings of graphs into that surface. What is the minimal number you need to color that surface? So let's have a look back here. As soon as I can embed a surface into something like the torus here, I can always talk about colorings. And in this case, I need 7 colorings. Why do I need 7 colorings? Well, I have a fixed hexagon here in the middle, and this was a horrible choice of a color. I have a fixed hexagon here in the middle, so all 6 around it should get different colors. So I need 7 colors, at least 7 colors to color this picture here. Okay, and you can ask the same for all surfaces. And the four-color theorem is a famous instance of it, and it's really, really hard. It's proven by computer. It was proven by computer eventually. We're still missing a good proof, whatever that means. So you might think at this point that it's just hopeless for a general surface. Turns out that the question for general surfaces gets easier, and this one is the hardest case to consider. And there's a closed formula, and it's called Heawood's formula. So the formula works unless you are in this strange case that your surface is, well, one of these, or the Klein bottle K. So Klein bottle for me is K. And the Klein bottle is a little bit weird. It's not hard, it's just weird. It doesn't fit into the formula. But otherwise, the chromatic number, the minimal number of colorings that you ever need for your surface, is given by a closed formula that only involves the Euler characteristic that we know by now very well, the Euler characteristic of the surface. So for example, for Euler characteristic 0, that's my little torus here. Well, let's see. This term dies. Square root of 49 is, I guess, 7. 7 plus 7 is 14 divided by 2. So this gives 7, which is exactly our picture from before with the 7 colors. And this formula proves that this is kind of the maximal color, the maximum number of colors we ever need for any graph that embeds into the torus. The formula is ridiculously efficient. It's absolutely great. So here it is. For any surface except those two, the formula is always optimal. The optimal value is always this one. Turns out that for the Klein bottle, it's not quite optimal. This was really bad because I want to use the other one as well. Turns out for the Klein bottle, it's not quite optimal. And turns out that for the plane, it's even worse. It gives 6, but the real value is 4. But anyway, this is impressive. There's a problem, the four-color problem, which looks impossible. And if you generalize it, it gets easier. You don't prove the four-color problem here, the four-color theorem, sadly, because the number you get is 6. But anyway, for anything else, it's easier. Well, unless you're on a Klein bottle, and turns out that people can do the Klein bottle by hand. And there's a graph that's called the Franklin graph, which is due to Franklin, what a surprise. And this is a graph kind of where you need 6 colors. Here's how it looks like, or embeds on the Klein bottle and you need 6 colors. Anyway, so the Klein-Butler is kind of a special case that you need to treat by hand, and the plane, like the four-color theorem, is really difficult. That kind of makes this theorem so amazing. Plane, the easiest surface, is really difficult. Everything else, ignoring the Klein-Butler, is kind of easy and comes in a closed formula. Okay, I hope you enjoyed this video on colorings of graphs on surfaces, and I also hope to see you next time.